Math 331 problem solving. This is lecture 9. And what I want to do today is talk about one of my favorite problems, the egg drop problem. Has anybody here seen this problem before? Excellent.
I don't know the F1, so the like physics-y one where like you get people that like
this is not the physics one, and this is not the one where I'm trying to measure the height of a building. Where the best one is I'll give you this beautiful protractor if you tell me the height of the building. It's not that one. And so what I want to do is I want to talk about a mathematical version. I've given this talk many times to people from college-age students all the way down to elementary school kids. And what I love is there's a lot of ways to do this problem. You can gather data, and it's also not clear exactly what problem you should be doing at first. I mean, again, I have to tell you something as the professor, but there's a little freedom in terms of what we actually study. So to give us some starting point, let's say we have two special golden eggs, and I spared no expense in changing the color of the text. And let's assume we have a building with n floors. If you want to think of n as like 100, some big number. And these are very strange eggs. No matter how many times you drop the egg, if you drop it below the critical floor at which it breaks, there is no damage done to the egg. You can drop it 1 billion times, and if it doesn't break in the first 15 floors, as long as you drop it on floors 1 through 15, no harm will happen. But if you drop it from the floor at which it breaks or higher, one drop is enough to completely destroy it. So the egg can be used as many times as you want below that critical floor where it breaks. And then once you drop it from the floor where it breaks or higher, one drop is enough to destroy it. Everybody understand these eggs? Okay, so the goal is to find in as few drops as possible, what is that critical floor for this building? It does not matter if you have any eggs left over at the end of the day. I'm not going to give you extra credit. I'm not going to give you $1 million. Yes.
I have seen it.
Okay, so if you've seen a version of this problem, then you have lost your voice at various times today. And I'm glad you didn't say yes. Excellent. So everybody understands we don't care about how many eggs we have left. We just care in finding in as few drops as possible where the critical threshold is. Okay. So how do you interpret finding n in as few drops as possible? What does that mean to you?
You can know with certainty the value of n.
Okay, so you want to know with certainty. I need to know for sure that this is the floor that it will break at this floor and nothing below. Okay, what else? How do you interpret as few drops as possible?
Does it mean as few cracks, or I'm interpreting it as few like throws, even if it doesn't crack, it counts as one.
Good. So even if it doesn't crack, it counts as one. Yes. But what does as few drops as possible mean?
The optimal, like as a minimum number of drops to reach a certain value n.
Okay, and how do you define minimum? My question is, are there any implicit assumptions we're making about this problem? And that's one of the reasons why I want to talk about this. What do you implicitly assume when you see something? What am I trying to minimize? I'm trying to minimize as few drops as possible. Minimize in what sense?
Drop should be like a non-negative.
Okay. Drops would be non-negative, but
Divine knowledge is just like something.
I don't know if this is what you're looking for, but shouldn't it be like it's like few guesses? Like you could figure it out in 2 drops if you like randomly guessed the first one. It broke and then you went one level up, but that wouldn't be like a bit.
Wait, if it breaks, you can't go one level up, because if it breaks, you just know that that's an upper bound.
If you happen to reach the exact
if you reach the exact number on the first one,
right,
and then you guess again the second one, that it's one above that. So you guess if it's 15.
Right.
The first one you hit 15. And then
and
the second guess you go 14. That's a minimum, but that's not a good solution.
But the problem with that is then that puts you at huge risk.
Yeah, which is why it's not like, I don't think that it would get you in as few drops as possible, but that's not the optimal solution.
Right, so this is where we need to balance the certainty. So if you had something like that, so what I mean when I'm saying as few drops as possible is there are two ways I think you could interpret this. You could minimize the worst case, or you could minimize the average case. And these are not necessarily the same thing. So when you're looking at a lot of computer algorithms, what are you trying to minimize? Are you trying to minimize the worst case in which that I have to run, or am I trying to minimize the average case?
Normally, we try to minimize the worst case.
Normally, we try to minimize the worst case, but for a lot of problems, that may be a very bad decision. You know, if the worst case happens so rarely, I might be willing to risk it to have a much better average runtime. And so this is one of the main points I want you to get out of today is really think about what you're trying to do when you see a problem like this, because very rare will they be very explicit in saying what we want you to do. Normally, we assume you are trying to minimize the worst case. We might then be making some kind of assumption about how the floors are chosen. In some problems that we might get to later in the semester, you have the diabolical math professor who hears all of your strategy sessions. And knowing what strategy you are using will deliberately choose the initial configurations to make things go as wrong as possible. But you could say, what if we assume that the floor at which it breaks is uniformly chosen at random? What strategy should we use under that case? And then the average case for that might be much better than the worst possible case. So again, just things to think about. Okay. Oops, it's not letting me advance. All right, there we go. All right, so whenever you're given a hard problem, general advice is to try to find an easier problem first. Typically, they don't give you the easy problem. They just start you off with something hard. So can we do a specific set of parameters? Can we simplify something? What do you think might be an easier problem to do 2 eggs and n floors?
Infinity eggs.
So one is you could have infinitely many eggs. You could increase the number of eggs.
Or n eggs.
Or n eggs and n floors.
I think you need infinity.
Good. So good. So you're once I have n eggs, unless I'm a complete idiot, I don't need. So one is to increase the number of eggs.
2 floors.
One is to decrease the number of floors. There's something else you could do rather than increasing the number of eggs or decreasing the number of floors.
Decrease number of eggs.
Decrease the number of eggs. What would be the simplest problem to do? 1 egg, right? Rather than trying to solve the problem with 2 eggs or even more eggs, let's solve it first with 1 egg. And then if we can do that, try to go up to 2. So if there's 1 egg, I'll let you think for a moment, and then the people who are watching this at home will be bored as you're thinking. Can somebody come up with a strategy that's guaranteed to work to find the floor? Right.
Yeah, you go from down drop.
Yeah, down top. Go 1, 2, 3, ... till crack. There's really not much we can do when we only have 1 egg. The problem is extremely straightforward. What happens as soon as, if you have 2 eggs, as soon as 1 egg breaks, what happens? We have to go to the strategy. This is the advantage of breaking it into a simpler case first. By knowing what happens once we have 1 egg, as soon as our egg cracks, if we have 2 of them, we now have to go floor by floor by floor. Okay, so now, so the only possibility is to go 1, 2, 3 until it breaks. The worst case is that it will take n drops. And that's just the floor is the final floor. And we have no choice but to go 1, 2, 3 if we want a strategy that's guaranteed to work. Okay, so it's worthwhile to keep track of what is the worst case time in these problems. Can you give me a theorem about how the worst case time changes as I increase the number of eggs?
I think if we use the first egg like right in the middle.
Don't give me anything involved. I want a simple theorem that you can easily prove that's true about the worst case time as we increase the number of eggs. Simplest thing that you can prove without any work. I'm sorry?
Same number of columns.
Same number of floors, n floors, but I increase the number of eggs.
N divided by E.
So now you're giving me something hard. You're giving me some big result.
It's just that it's at the worst case, then you have to get 1/8. Like the number of eggs reduces the worst case.
Almost, but not quite.
It's the same always.
It's the same or less. As a trivial result, if I add more eggs, the worst case scenario can't become larger. So whatever analysis I do, I know I'm looking in the back of my mind, it can't get worse as I add more eggs. And I expect it should get better. I expect it should get better up to a certain point. We had the wonderful optimism of having infinitely many eggs. And that's actually useful now. Because we talked about how once we have n eggs and n floors, those extra eggs don't matter. It's not going to do anything to the worst case runtime. So your comment was actually very prescient about what was going to happen later. We do not expect that the runtime is going to constantly decrease as we add more eggs. At some critical point, adding more eggs will not help. There's a very famous problem, the security guard problem. If you have a museum and you have security guards, what is the point of the security guard? To keep it safe. And so the first security guard you hire adds a lot of value. But after a while, adding additional security guards does not really add anything. And so do you have every painting always under view of a security guard? I will not say if I have gone to a museum in, let's say, 50 miles of Williamstown with some family members where they looked at the artwork and I looked at the patterns of security guards to notice, was there a part that was missed by the movements where every now and then there was one little wall. And I will not say if I did this, and I will not say if I did that where that museum is, where there could be a wall that's just missed for a very small period of time because of the movements of people. So then you have to ask yourself, is it worth having every painting protected at every moment? How much time can you have something unprotected? How much does it cost you to hire these additional security guards? And a lot of times what you can do is you could have somebody on the boundaries of two different rooms. They look at a room, they see nobody's really doing anything, and they can turn, look at the other room, and turn back fairly quickly. And the amount of time that things are, well, if somebody has a can of spray paint or something like that, that could be enough time to do some damage. So you have to really ask yourself, and this is why you will often see one person per room, and you will have them in very specific places where they can see. People will be at boundaries of rooms. But you do reach the point of decreasing returns to eventually it can get to the point where you have negative returns. I have spent 6 years working in restaurants. If you are the only chef and it's busy, it's bad. It's helpful to have more chefs. At some point, if you have 300 chefs in the kitchen, you're getting in each other's way, no one can cook, and it's actually worse. So you want to think about issues like this. Okay, so now let's say we have 2 eggs. Once one egg cracks, we know we reduce to the 1 egg case. So the question is, what are the possible strategies when you have 2 eggs? And so what I'll do now is I will pause for a moment to just give everybody a chance to think for a little bit. All right, so we are back and hopefully everybody has their strategies. What is your strategy with 2 eggs?
Something like a binary search.
Okay, so where do you drop your first egg?
Maybe in the half height.
Okay, so you drop in the half height. If it cracks, what do you do?
If it cracks, you go lower.
Where do you go?
I mean, if you go to the lowest point, you go up.
Okay, good. And if it doesn't crack, what do you do?
You go from the half height up.
To where? So if it didn't crack at, say, 50 out of 100, where do you do your next one?
51.
We're on 75.
Yeah.
Go to the next half.
So if your first egg doesn't crack at 50,
But how about like 2 eggs?
you have 2 eggs, right? So if your first egg doesn't crack at 50, you still have 2 eggs.
Oh, I still have 2 eggs. Then,
Right.
Yeah, then you go 1 half up.
Well, so then you go to 75. And if that doesn't crack, where would you go? Approximately,
87.
yeah, something like that. So you would do like a binary search. That's one strategy. Do you have another strategy?
2, 4.
2, 4, 6. This is wonderful. You guys are complete extremes of each other. All right. And so coincidentally, that happens to be what the next slide is. Right? I've given this talk before. these are the two natural strategies. One is to drop every second floor. I had the order wrong. I thought people would have said the even floors because I should have called on you. But I was worried after the infinitely many eggs that you'd be a higher number. And so the other one is to drop at the halfway point. What's good about dropping every second floor?
Higher likelihood that you keep the eggs alive, and it's like very easy to figure out the next one.
Good. So
Less chance.
once your egg cracks, you really have localized where to go next. What's good about your strategy? Where you dropped at the halfway point. Why might this be a good idea?
Because the search complexity is like it's the average search complexity of that. I mean, I don't know what's the average.
Well, what's good about dropping it halfway?
Or you immediately like eliminate half.
If it doesn't crack, you eliminate half. So if it doesn't crack, you've eliminated 50%. If it cracks, you're screwed.
I think you can improve on the N/2 strategy by dropping it at N/3.
Ah, okay. So now the question is, where do we want to drop it? So one is to drop every 2, one is to drop halfway and do a binary search. One could be N/3. And then if that cracks, then you have to go one at a time. If it doesn't crack, would you do 1/3 of what remains?
I would do 1/2 of what remains, so I'd go up to 2/3.
You do one, so you would do 1/3 the first time, then 1/2 the second time?
So I would do like 33 the first time, and then I would.
No, but once the first one doesn't crack, it doesn't crack on the first one.
Yeah.
You now have a new game with just a new number of floors.
Oh, well, then I guess I would do 1/3 again.
So your strategy should not be changing,
Yeah.
right? So this is the whole point of this problem. And I'm actually supervising a thesis where we have an issue like this. This is a huge tendency humans have, is to lock yourself in to things you've already started and not realize that it doesn't matter that I was doing this. It's a new game right now. It doesn't matter how I got here. Once you drop that first egg, if it doesn't crack, you now have a new 2-egg problem with fewer floors. Don't consider those floors at the beginning where you know it's not going to break. You don't have end floors anymore. Now you have 2/3 end floors. Where do you drop your first egg there? And so if you're saying that your best strategy is to drop 1/3 of the way, then it should always be 1/3 of the way. You shouldn't be varying that.
Yeah, makes sense.
So the drop should be a function of the number of floors. Now the question is it a simple multiplicative rescaling or is it something more involved? And for small data, it's not going to be clear what that is. So I'm hoping that what you will accept as a generalization is we could drop every X floors. But again, to some extent, we do want to dynamically change things that if things don't break, we have a new problem. And that's why you're dropping over N/2. In some sense, it's really not going to be dropping a fixed number of floors every single time, because if it doesn't crack, we've rescaled the number of floors. All right, but let me look at the worst case of those two extremes. What's the worst case if you drop every 2? So the worst case is that it's the last floor that's the bad one. If you drop at the midpoint, what's the worst case?
Is that the worst case that it's the second to last one?
Yes, yeah. I mean, okay, so I'm a mathematician, and whenever I lecture in public, 1 = 0 equals, I'm going to be accurate to within 1. I do not want to, when you write the paper, you have to be careful. But right now, yes, technically the worst case would be if it's 1 less than n, because you would drop at n,
And
and then you'd have to drop back 1.
Where it depends if you're
Right. And so, and so we don't want to worry about that. What's the worst case if you drop in the middle?
N/2, but you break it in.
Yeah, that you break right then. And in fact, that was the first time it breaks, and then you have to go all the way back. Because if it doesn't break then you drop another halfway up. So when we're trying to analyze the worst case, worst case, if we do every 2, it's basically N/2 drops, and then +1, I think. And then if halfway, that's basically oops. So if it's halfway, we have one drop initially. And now we have n over 2 minus 1 floors, and we have to do one at a time.
Isn't the worst case for the halfway too also if it's the top one?
No, because if it's the top one, we drop it first, and we eliminate half of the floors. Say we eliminate 50 floors.
Yeah.
Then we drop it at 75, and we eliminate
Oh,
half
'cause
as
we're-
well.
Yeah, 'cause we're at 75.
So it's going to be,
Yeah.
it'll be like the log of n number of drops, log of n base 2 number of drops. So if it is, the worst case for us is if it's going to be halfway. So I think it's going to be one drop for that first egg. And now I have n over 2 minus 1 floors that I have to check. So I think it's something like this. So because we're saying 1 equals 0, these two are basically as good as each other. So you can both feel good about yourselves, and neither one of you should be able to feel better than the other. What if we did every x floors? What's the worst case then? Yes.
N over x plus x minus 1.
Good. So n over x. So again, it's going to be the worst case is going to be when it's the last floor. So then there's n over x floors. And then we have the x minus 1.
We could also get, depending on the x's, if the breaks on that first floor could be x minus 1. Could just be.
Yes.
Or like,
Okay. Good.
yeah, no, it could just be x. It would be just
Or it could break on the first one and then x minus 1. So x should not be greater than n halves. Because if we're doing it in jumps of x, if x is on like 90% of n, but you're right, we should think this, if x is huge relative to n. We're not going to choose an x that's huge relative to n. But these are the two extremes. So which do you think is going to be better, n over 2 or n over x plus x minus 1? And when I'm looking at this, this is really n over x, n over x plus x minus 1. It's the n over x plus x that really matters. Do you think there's going to be a choice of x that's going to be better than x equals 2? Yeah.
There's some like inequality relating it.
There's some inequality relating this. What I like about this is you have two competing influences. So what's nice is each of your methods has something at its disposal. Your method, by going all the evens, is wonderful in that once the egg cracks, then you have very little work to do. You've localized the problem. The difficulty is it could take a long time for you to get to the point where you localize. Your method is terrific in that whenever it doesn't crack, you've eliminated a huge number of floors. But as soon as it cracks, you now have a large number of things and you have to check them one at a time. So you have two wildly different methods. What should we try to do? And we have two wildly different methods that each have something good. Combine them in some way. And in fact, that's what the n over x plus x is doing. The n over x is if you check every x floors, the worst case is you have to do n over x checks from that. And then you have to do x minus 1 checks from the remaining egg. And so we have two competing influences. We want to try to combine them. So we want to make both of them small. Not going to happen. The smaller you make n over x, the larger you make x.
Do we assume uniform distribution?
For which floor is bad? No, you assume I'm evil. And just whatever makes things as bad as possible, that's going to be where it is. Normally the students don't have any issues with that assumption about me. That probably means something, but I'll leave that for a future lecture.
Or the art gallery security guards.
Or the art gallery security guards, yes. Interestingly, I am going to the clock later today to meet a Williams alone. So we have two competing influences. We want to make n over x small, but the smaller we make that, the larger we make x. We want to make x small, but the smaller we make that, the larger we make n over x. Okay. Then the next slides over here is basically just writing down formally what we did. We have the competing influences dropping every x floors, which we've talked about. And then we have this function n over x plus x that we want to try to maximize. I try to minimize. I'm not really worrying about the -1 because that's fixed. All right. And so what we can do is, one way we can do it is to say, look, we've got two terms. Let's set them equal to each other. This is not guaranteed to give you the best choice, the choice of x that will make things as small as possible. But it's a simple, easy choice to do. And for a lot of complicated problems in mathematics, I am quite happy to do something simple and maybe get close to a solution, especially if it gives me a closed form expression. And so if I set the two of them equal, I get n over x equals x, so n equals x squared. This is not a difficult problem to solve. X is the square root of n. And so if I'm dropping a fixed number of floors, I would choose to be the square root of n. This is not a good thing to do, because as soon as the first egg doesn't crack, I should rescale because my building is smaller. I shouldn't be committing myself to dropping a fixed number of floors. But again, I'm trying to just do an easy strategy to implement. For those of you who are taking computer science, you can just immediately do some kind of recursion, pull it up, decrease the floor size, and rerun it with that. Okay, can anybody think of another way other than setting the two of them equal to try to figure out where this is smallest?
I'll take the derivative.
Yeah, so I've mentioned that I've given this problem to college students as well as to elementary school kids. Most elementary school kids do not know calculus. It's disgraceful, what's going on. If you watch Star Trek in the future, they finally start teaching calculus at a much younger age. But nowadays, you can't really assume third graders know calculus. But equating things, that's not so bad. And that's one of the reasons why we have 100 floors, right?
I think it's going to be almost the same.
So for this problem, it will be the same. Now, what's interesting about this is, if we plot at 100, you can look at the plot and it does look pretty convincing that 10 is going to be the minimum. Is it going to be the square root? I would have to do this again, not with 100, but with maybe 101, 102, 103, 104. And so there it is suggesting that we need to use some calculus, but there's some good ways to look at problems like this. So one is, we've talked a little bit about rescaling. What's the natural scale for this problem? It should be clear at this point that the square root of the number of floors seems to be the right scale to study things. So instead of letting x be where we drop it, let's write x as t times the square root of n. And if we put that into our function, notice now that the two terms have an n to the 1/2 that we can pull out. And it's now just n to the 1/2 times the quantity 1 over t plus t. And by doing it like this, we've now pulled out the dependence on the number of floors, and now we just have a universal function to minimize, 1 over t plus t. How do we minimize that? Well, we can use calculus, right? And if we use calculus, you will get that the minimum occurs when t equals 1. There is another way that we can minimize this using some work we have done for over a week in this class. How can we minimize? What can you tell me about 1 over t plus t? We want to minimize this, right? I was about to draw a hint. Can you get it without the hint?
Is it connected to the thing we did with minimizing the fences?
Somewhat.
Like another case of this problem that we just did.
Not quite.
Multiply over t.
Good, and if you multiply 1 over t and see what you get. So instead of minimizing this sum, what if I minimize the sum over 2? This is the AMGM inequality, right?
It's the AMG from tomato, like, nah, it's gonna be a joke.
No, 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 no.
How do we find the AMG in here? This can't be right.
And just note that 1 over t times t equals 1. So the geometric mean is 1. So the arithmetic mean is at least 1. Is 1 if t equals 1. So that has to be the minimum. So here's a nice way to use the arithmetic mean, geometric mean, which we spent several days doing. This is not something I do with the elementary school kids, but since we've been fortunate enough to talk about the arithmetic mean, geometric mean, I know from that 1 over t plus t will be minimized when t equals 1. Even if I didn't, I've reduced the problem now to there is some value of t that minimizes the sum. Clearly, as t gets large, this goes off to infinity. As t gets small, it goes off to infinity. There's going to be some critical value. T equals 1 makes sense because it's that transition point between the two. But the point is, we were able to sniff out how it depends on the floor. And so now, how expensive is it? What's the cost if we have 2 eggs as a function of the number of floors? So about how many drops does it take us if we use this method? Approximately. So if you choose the best value of t, about how many drops is it going to take us? About 2 square roots of n. I'm not going to worry about the -1 and stuff like that. But worst case, the number of drops is going to be like 2 square roots of n. When we had 1 egg, how many drops was it? Worst case, approximately n. Then it was about 2 root n, right? So let's see, do I have? Okay, so again, if we know calculus, we can do stuff like this. I'm going to just do a little table. Number of eggs, worst case. When there's 1 egg, it's n. When there's 2 eggs, it's 2n to the 1/2. Anybody want to guess 3 eggs?
Completely unrigorously, is it 3n cubed? I mean, sorry, cube root.
That is definitely a possibility. So do you think it's going to be like n to the 1/3? Do you think it's going to be 3 outside? We definitely know the first 2. And again, I should put worst case in quotes because that's using this method. Yes.
It seems to also fit with like understanding that as we add more and more eggs, there is some point at which adding more eggs doesn't help us anymore. And because constant terms increasing as we decrease the power,
Right.
like there is definitely some point where the next is going to be greater.
Right. I mean, it definitely seems like a reasonable thing to conjecture. Are you more confident on the exponent of 1/3 or the constant of 3? Or are you equally confident?
I can see it going to 1/4.
You can see going to 1/4.
I can see it going to 1/4, or I can see it going.
I can see a lot. I can see a lot of things with just 2 data points.
Yeah.
And so is it really 3 and 1/3?
It would fit more if it was 4 and 1/3.
What should we do?
But you hit that limit quicker.
What should we do?
Check.
How?
Try adding 3 eggs.
Try adding 3 eggs, right? Let's look at 3 eggs. So to just put what we're doing in context, what we're really doing is we're balancing algorithms. So imagine you have 2 algorithms. One algorithm always takes 1,000 seconds to run. And the second algorithm takes 1 second, except once every million inputs, it takes, is that a billion? Takes 1 billion seconds. Which algorithm would you want to use?
Minimizing the worst case for average case.
Right. And so if I want to roll the die, I could just do algorithm 1. No, that's 1,000 seconds. If I want to just roll the die, let me do algorithm 2. Once in a billion, I'm going to be in trouble. If you haven't read about the Intel Pentium bug, do so tonight, about how small little things can cause huge issues. A much better approach is to balance them. Take algorithm 2. Wait 2 seconds. If it hasn't terminated, switch to algorithm 1. Then you protect yourself, and you can get your average runtime to be almost a second. So if you do some kind of toggling, then you're going to be fine. So this is a really good idea to dynamically adjust what you're doing based on how things are going. I have an algorithm that works most of the time, and I'm fortunate that if I'm in one of the situations where it doesn't work quickly, I know that immediately. If it runs quickly. So I let it run, and if it doesn't run quickly, then I stop using that, and then I go to the slow methodical thing, which I know will work. Okay. So now we can improve things a little bit with the standard approach with 2 eggs. I'm not going to go into too much detail right now. I'll leave this for you to think about of adjusting using triangle numbers. And this is taking into account a little bit the fact that as soon as one of the eggs doesn't crack, we should adjust the size of the building. And so I'll just leave it as a small improvement. It's not going to change the order of magnitude of things. But again, 105 is not a random number. It's a triangle number. I think 14 plus 13 plus 12 all the way down to plus 1. And I dropped the first one at 14. And if it cracks, it's going to take me 13 more drops to figure out what goes on. That's where the 1 plus 13 comes from. I drop it. If it cracks, it then takes me 13 drops to do the next. Now, imagine it doesn't crack on the first drop. I dropped it at floor 14. I now drop it at floor 27. And now imagine that it cracks. Now, because I moved up 13 floors, I now only have 12 more drops to do. Notice that these numbers are the same. 1 plus 13 is the same as 2 plus 12. So before, when we were dropping it every x, if it didn't crack until the very end, I had a large number of drops, and then I have to do one at a time. It's better to drop a little bit higher at first, so that if it cracks, okay, I then have more to check. But if it doesn't crack until later, I've eliminated more. And so the amount I have to check is going to be better. So this is a slightly better approach. It still gives you something on the order of the square root of the number of floors. It's not going to change the power, but you can do some games with the constants. All right, so what if we have 3 eggs? So do you want a few moments to think about your strategy? Or does anybody want to just yell out a strategy right now what we should do? Yes.
I haven't considered this problem at all.
Okay. Okay. So there's lots of ways we can do this. A lot of times as a professor, I don't care about the optimal, I care about what can I explain and discuss easily. Let's try to take the 2-dimensional strategy and do it as simply as possible. Let's drop every egg floors. So drop every x floors till crack. Then it's a 2-egg problem. So what's the worst case if we drop every x? How many drops do we have before the first egg cracks? N over x. And now we have the worst case of 2 eggs and how many floors? Not x floors. Close. X minus 1 floors. And again, this is where I don't really want to worry about x versus x minus 1, but technically, this is what we now have. What is the runtime, the worst case scenario, if we have n floors? We just said it was 2 square roots of n, right? So this would be n over x plus 2 square roots of x minus 1. Does anybody really want to do square root of x minus 1? What should we do? square root of x. And so how would we optimize that? So we want to minimize this. And again, I don't care if you give me the actual minimum. Can you give me a method that will give me something that should be reasonable? That I can do the algebra without making a mistake. Yes, set them equal to each other. So if n over x equals 2x to the 1/2, then you're going to get n is equal to 2x. And what happens when we bring that x over? We have 3/2. So x is equal to, let's see, it's going to be n divided by 2 to the 2/3 power. And then how do you feel how bad the runtime is? The worst case scenario. And so do I have to evaluate both expressions? So yes, I substitute x equals n/2 to the 2/3 into both of them. Do I have to evaluate both of them? What do we know about those two values? We've just assumed they're equal to each other, right? So because of this analysis, so worst case is going to be just twice. So which do you want to do? N divided by x or 2 times the square root of x? I'd probably rather do 2 times the square root of x. So, but it doesn't matter. So we'll then get n over 2 to the 2/3 to the 1/2. Okay. So we're going to get a 2 to the, well, I'll do it slowly. 2 times n to the 1/3, and then down below, we're going to get 2 to the 1/3. So did I do it? Missing 2. Did I make a mistake?
I thought like.
Oh, no. Well, that's what this 2 is outside of. Oh, I'm sorry. That 2 is from, you're right. There should be another 2 there. Thank you. 2 times 2. So 2 squared. So then this should be 5/3. Thank you. And how does 2 to the 5/3 compare to 3?
Well, 6/3 is.
6/3 would be 4. So we know it's less than 4. So it's a little bit of work to see, is this less than or equal to? But again, this isn't minimizing it, right? What should we really do? Okay, so it would be, what we really have is we could say f of x, it was n over x plus, I think 2x to the 1/2. I think that was the function we had. So we could do f prime of x. Okay, when we take the derivative, it's going to be negative n over x squared, right? Plus 2 times 1/2 is going to be x to the minus 1/2. Have I done the algebra correctly? Yes? And I don't have to worry about endpoints. So f prime of x equals 0 implies n over x squared equals x to the 1/2, or n equals x to the, to the negative 1/2, to the, multiplied by that's going to be x to the 3/2. So x is equal to n to the 2/3. So it's the same order of magnitude, but it's a different constant. So yields, worst case is going to be n over n to the 2/3 plus 2 n to the 2/3 to the 1/2. Oh, this is looking a lot better. What do you get now? 3n to the 1/3. So can you then continue? Can you prove by induction that it's always going to be, kn to the 1/k? Or if you can't get the constant k, can you prove that there's some constant? So prove there exists constants e sub k for egg such that with k eggs, worst case is going to be less than equal to e sub k times n to the 1/k. So you should be able to prove that by induction. And then the question is, what can you say about that? This doesn't prove that this is the best you can do. It just proves if we're always going to drop at every x floors and not dynamically rescale and not take into account the fact that as soon as the first egg doesn't crack, we know that the build. So maybe if we somehow use triangle numbers or things like that, we can do a little bit better. I don't care. Anybody who does computer science, and I know there's a couple of you right now, you frequently care more about how does it scale with a key parameter of interest and not that little arbitrary constant outside. This is giving us the dependence on the number of floors. And you should be able to prove that it's growing like n to the 1/k. That's not bad. So this is one of my favorite problems. There's so much good mathematics in this, a lot of good computer science, a lot of good problem solving, a lot of how do I want to look at things. There's also ways to solve in levels of solutions. If you want to do a quick, simple solution, I've got two competing influences, make them equal to each other. That's not necessarily going to be the best, but frequently it gives you a really good order of magnitude approximation that's going to be close enough for what you need to do to give you a feel for the behavior. If you then want to try to optimize the constants, that's often your several advanced research papers as to what's the best you can do. But the exponent, we're able to get that very quickly without using calculus, and it gives you a sense of just how deep things are. All right, so that is a good place to stop. I will stick around in case anybody has any questions.